Thanks a lot, guys, for joining this session. My name is Ranjit Mahalikuri. I work as a director of energy storage at BrightNight. So we're a large-scale independent power producer where we basically build utility-scale solar and wind farms along with battery energy storage, especially for a lot of our utility customers for renewable capacity for the grid. And my topic today will basically be a few high level overview of, from an IPP or a developer point of view, what are the current prevalent energy storage technologies that we have today? Then going down into some battery technology innovation that I'm personally seeing at the cell level and the system level that some of the amazing battery engineers are working on that is actually having a huge material impact on cost and performance and just how quickly you can deploy these sites nowadays. Also go into a bit of the technical side where we'll talk about some of the battery sizing guidelines that we typically use when we design these systems. How do we think about augmentations and planning for future additions of battery capacity when these things start to degrade over time? And I also thought it'll be good to talk a bit on the commercial side, where this has been a huge topic of late, where as a developer looking to buy and operate these assets over like the next 15-20 years, it's become really important to know where the battery materials are coming from, what's the raw materials that are really sensitive to the price of the equipment that we buy today, and also a bit of commentary on US regulatory policy updates that have recently happened in the past couple of months that is both a benefit and some that are a challenge to this industry. So just a quick overview. When we talk about grid scale battery storage, I like to give the analogy of, ancient humans when they were evolving and they try to, store food, right, during seasons. When food of a particular crop is very prevalent during like the summer or spring seasons, and you don't have that growing during the winter time, there is a need for storing this food either in granaries or some sort of storage where it keeps it safe and clean and away from pests and other things. Well, energy storage for the grid is essentially like that. You're matching supply of energy on one side, either whether it's from renewables or nuclear or even coal and natural gas, and linking it to the demand side, which is residential customers and commercial and industries as well. So with the onset of renewables, the penetration of renewables going up over time and continuing to do so over the next couple of years, we really noticed that there is a much bigger need for this kind of matching supply and demand because renewables are intermittent over time, right? So battery storage basically enables us to do that. And there are different technologies that are out there. And I personally like to categorize them into what I call sprinters, the marathon storage runners, and the ultra marathon storage technologies, right? So sprinters are the most common ones that we see today that's being deployed on the grid. You can think of your typical lithium-ion batteries that are going into your phone or your electric vehicles, but much bigger in size, much higher in voltage and power requirements and energy capacity, where developers like BrightNight and other companies, we buy these grid scale batteries from original equipment manufacturers like Tesla and CATL and Fluence and other companies. And they're really well suited for having a really high round trip efficiency because you want it to be able to be really efficient when charging renewables and not wasting any of that because you're going to be operating this almost every day. It's really ideal for your daily shifting of energy where you have the solar peak that's happening during the middle of the day. You'd want to store that and then have that meet demand when the sun goes down in the evenings. And these kind of battery technologies work really well where they're quite high efficient, they're really quick to start up, they're really easy right now in terms of cost and constructability to deploy and pair with wind and PV sites as well. The next category that we are slowly seeing come into the industry are these marathon storage technologies, which uh, the energy efficiency is not as good, not as high as lithium ion in the 80s or 90% round trip, but something in the lower 50s or 60s. But one of the key advantage of these technologies is being able to hold this charge over a long time, not have very high auxiliary loads or cooling losses, and have really low capex and low throughput cost of energy. Right? You want to use these batteries where you will not have generation over a couple of days, and lithium ion really is not suited for that because of just how expensive it gets when you have to scale it over durations more than 4 to 8 hours of storage. So, a few examples of these, we're seeing like a lot of iron air batteries that are coming into the market space, especially from farm energy, which is making a lot of waves recently. And flow batteries have always been there, and they're also like trying to make some headway into this category as well. And finally, one of the biggest ones that we need in order to like transition to a fully 100% renewable grid is having these storage technologies that can fill in gaps over seasons, right? You have a lot of solar sites in the US, especially California, where the solar resource is really good during the summer, but over time in the
Hey,
winter.
Ranjit.
Yep.
Sorry, I don't think we're seeing the slides moving. So if you've got it in presentation mode or two different screens, can you make sure that you are flipping through slides because we only see
Yeah.
slide one. So
Which one do you? Okay, is it flipping right now?
no, actually not. We don't see it.
No, we're looking at the first slide only.
Oh, okay. Thanks for flagging that. Let me try to reshare. Thank you.
There we go. It just changed.
You see move. Yeah.
Yeah, I think we're on 6 now. So yeah.
Okay. Maybe I'll just stick to like this
This
smaller.
works fine. We can see it. Just go through
Yeah,
it.
this is fine. Yeah, this works. Thanks.
Okay, thank you guys. So yeah, I was basically talking about this one. I think this visually looks a lot more better than just hearing my words. But yeah, I was categorizing. I like to categorize this into these three energy storage Olympic participants, right? Which are sprinters, marathon runners, and ultra marathon storage technologies. And we've also seen them be categorized in terms of the technology itself and what kind of chemistry they use, or whether they're based out of thermal storage or gravity storage. And so, as a developer, what we try to do is we work really closely with utilities, especially in the US, but also in different parts of the world, where we try to work with utilities to understand what the value proposition is that energy storage brings to their grid. Right now, you have generation technologies like solar and wind that are producing the energy, but over time, as more and more solar gets installed in the grid, energy is going to become a commoditized resource. All developers are going to be fighting for the lowest cost of energy. There's going to be a lot of energy on the grid. And what the grid really needs in the future, as you have more and more intermittent renewables, is firm capacity. How do you shift energy during times of high supply to the times where the demand is really high and you can provide the firm capacity? It's more about keeping the lights on rather than keeping the lights running over a certain period of time with energy, right? So when we look at other advantages that battery technologies bring to the grid, which is transmission and distribution side, where you do not have to build out really expensive transmission lines or upgrade utility lines because of how much more cheaper and quicker it is to install and construct utility scale energy storage projects. Usually takes about 15 months or so for some of the ones that are on 1 gigawatt hours, but easily done within like 9 months or lesser as well. When we look at a developer such as BrightNight or others, we typically follow three main offtake agreements with utility scale batteries. We look at long-term power purchase agreements or tolling agreement where the utility pays a fixed capacity fee for use of the capacity, for use of shifting solar energy to later hours. There are very particular operating parameters around this, how many times they can cycle in a day, what are their operating temperature requirements, what's the ramp rate look like. And we as a developer, we make sure that utilities are staying within that band. As we know, batteries still right now are very sensitive to how they're operated, how they're cycled through a particular day or through their entire useful life as well. And in terms of cost, obviously, we look at the total cost of ownership, right? One of the most challenging things here is you're not just buying batteries and looking at the upfront cost of the system, but how much does it cost to own and operate over 15, 20 years of this useful life of the system? So we're really projecting what the battery performance will be like 20 years down the line, what kind of operating costs will it incur in terms of like cooling loads, in terms of augmentations, in terms of regular maintenance and replacement of parts. So it's really important to understand what's the total cost of the ownership of this entire asset. And lithium ion batteries are still fairly new in terms of whether they've been running for more than 5 or 10 years. So this is still something that are a lot of open questions on whether they're going to degrade at the rate that they've expected to. Are they going to be as efficient as the data sheet suggests? Are they actually going to cost X amount to operate over the next 20 years? And so that's some of the things that we run a lot of financial modeling on to make sure that the systems that we're buying and operating are able to stay within the costs that we project. Other ways that we can deploy these large utility scale batteries with utilities are with bill transfer agreements, where some utilities actually prefer to just buy the site outright and have them own and operate it. Is less sensitive to like total ownership costs and operating costs, but this is also a model that we've done. The final one, again, is a merchant battery, which is very prevalent in regions like Texas and California. There's usually no fixed term contract for like capacity or anything, but power producers own and operate this asset in the wholesale energy market, where it's a lot more riskier because you're really playing against the daytime and the day ahead energy market, but it does give you a lot more incentive for higher profit. And usually you see these batteries operate at a much higher cycle rate because they're trying to like recoup their investments within the next 5 to 8 years. Slightly different from long-term power purchase agreements, where these are more of set tolling agreements similar to like a car lease, right? Where you have a certain mileage that you're supposed to operate under. You pay the leasing company a fixed amount every month or every year, and you get to use all the attributes of that particular asset, whether it's providing firm capacity during times of need or ancillary services or other grid-related functions as well. Moving on, I wanted to talk about some of the innovations that I've been seeing from our amazing battery cell engineers from different OEMs. And being a developer, we are, apart from EVs, we are one of the most downstream customers of the entire battery supply chain. So when we work closely with batteries, I'm looking more at a system level of how do these systems operate within a grid, within how do they interconnect to the grid, right? It's not that I spend too much time looking at what happens at the cell level or what innovations are happening at the cathode and the anode, and being very particular about it. But in recent times, one of the amazing advancements we're seeing is in usually energy density, cycle life, chemistry, and form factor of these cells, right? So I wanted to touch into the innovations that we're seeing in the cell level and how that is translated down and flow down into really significant savings when we're deploying utility scale batteries for the grid. Energy density used to be something that needed to be chased for, especially with EVs, right? You wanted cars to have a really low, really high gravimetric energy density, where the energy per weight ratio was pretty high. So your cars have a lot of range. So there a lot of innovation was going on there. And interestingly, we've seen a lot of innovations on the utility scale side where we're not too worried about the weight of batteries unless we're transporting them on a truck. But the volumetric density of batteries was started becoming a huge thing. As you know, we these are spread across like acres and acres of land. Land is pretty expensive. These are heavy things which require a lot of foundation cost, excavating the ground up, putting in cables. And what we're seeing is that in recent times, the cell form factor and the energy density of per single cells have gone up significantly, right? So 5 years down the line, I was looking at the 280 amp hour cell as being the standard industry offering, where there's pretty much what everyone from CATL to EVE and other major cell suppliers from China were offering. And within just the short span of 1 year or 2 years, with a lot of innovations in how these cells were manufactured, with making them more efficient in terms of packaging, within the same dimensions of the 280 amp hour battery cell, we've actually seen the industry transform really quickly into a much larger cell amperage, which actually had a lot of cost savings on the utility scale side, where we basically had to deploy much less number of enclosures. There were much less number of cells that were sitting in a particular site. And a typical site for us is, say, more than 800 megawatt hours to a gigawatt hour nowadays, right? And each cell that you have is another point of failure in the system. It's another point to collect data from, monitor its temperature, current, and voltage, and carry spare parts on site. So with cells becoming much more energy dense for the same dimensions, we've seen significant cost savings on how efficient it is to deploy these systems at such a large utility scale. So that's one of the big things that where innovations at the cell level and the module level have really flown down all the way down to the system level, where we're seeing really material improvements in cost and performance as well. One of the other things that we are seeing is, of course, on cycle life, where utility scale batteries have a pretty rigorous operating use case, where they're usually called upon to cycle almost every day. And these are not just small swings in state of charge, but usually a full charge all the way up to a 100%, and then discharge all the way down to a 0%. So this does take a pretty big toll on the battery cycle life and the calendar life as well. I think in the next coming years, we will see more and more transition towards utilities who want more flexibility in how they cycle, right? Today, they have a fair idea that, okay, I may want to cycle the battery once a day, but we are actually seeing a lot of utilities wanting to cycle twice a day, where they have an evening peak right after the sun goes down and even a morning peak right before the sun comes up. So we're slowly starting to see the transition towards 4 and 8 hour batteries, which can be met with lithium ion at a pretty good cost as well. We're also seeing more flexible cycle requirements. And so it'll be interesting to see how, as the industry clearly creates a product line for utility ESS batteries and electric vehicle batteries, you will see more specialization in the cycle life and performance of utility scale batteries. And I think that's great for the industry. So far, we've been piggybacking on innovations that were dominant in electric vehicles and trying to, say, reduce weight, improve energy density. But we'll slowly start to see some companies such as Lithium already investing a lot in research and development into making batteries that are that are required just for grid scale applications and not for EVs. So when we see that specialization start to happen, I think there'll be a lot more improvements at the system level, and costs would go down, and the total cost of ownership of these assets over time will also go down as well. Um, in terms of chemistry, of course, lithium iron phosphate is still the king. We've slowly transitioned from NMC technologies to LFP, and really it just hits the sweet spot in terms of the cost at which a lot of Chinese companies have been able to bring down the safety of lithium iron phosphate when it comes to thermal runaway. Cycle life has been much longer as well, and the energy density, although was a flaw a couple of years back, we're seeing the energy density improvements also leapfrog ahead of NMC and other competitors. So LFP chemistry is something that is going to be there for and want to stay for the next couple of years. You also spoke about a quick highlight on form factor, with prismatic cells being one of the most dominant right now, just due to their good balance of energy density and safety and stability as well over like the entire operating voltage and the state of charge of it as well. One thing that constantly I keep thinking about is there a physical limit to how much the cell capacities can increase over time? Obviously, cooling requirements for these batteries start to go up. Is it going to be a lot more unsafe? Would it impact, say, the degradation and heat dissipation rates of these batteries? Would it require a lot heavier power systems and other studies that have to be done on the inverter side and the grid side as batteries start to get more and more energy dense? I think there's also a limitation on how big of a battery, how heavy of something that you can transport on our roadways. So there is another physical limitations there as well. So it'll be interesting to see how these innovations at the cell level slowly start to get translated at the system level, where we're deploying these grid scale systems. And yeah, I'm curious to hear you guys' thoughts as well on any of these innovations that we could chat about at the end of this discussion. Any questions on this? I could probably stay here for a while if anyone's curious. Okay. One of the other things that I've been noticing recently from a developer point of view is we spoke about innovations at the cell level, where we talked about energy density, we talked about chemistry, and most of what we do in terms of design and operations and how we construct and build these projects is actually more on the system level. We don't think of the battery system as just a cell or a module, but how all of these cells, millions of cells, and all of these inverters come together as a single unified system and operate efficiently over the life of the project. I've been seeing initially when I started working about 5 years ago, the DC block was one of the most more dominant technologies at that time. Obviously, before that, actually, the AC block. Firstly, let me talk about the two differences, right? A DC block is where you have a 20 or a 30 feet battery enclosure, and the output of this is basically just the DC battery that is reaching a system voltage of about 1500 volts or so. And the AC block is very similar. It's again a 20 to 30 feet enclosure with all the cooling and the power electronics, but the only difference is that it comes integrated with inverters. So you have the output of these batteries already AC, so you just have to step it up with a transformer and you're good to like start sending energy to the grid. It definitely sounds a lot more easier to install, so there are like clear advantages and disadvantages with the two types of system architectures that we're talking about here. I think it was about 5 years ago where the industry was more focused on the DC block approach because of the flexibility that it gave when it came to using different battery vendors, the flexibility that it gave in terms of design and pairing with different inverters of your choice. Inverters were starting to go down in cost as well. There were a lot of attractive and competitive offerings in the marketplace, which trended towards, and also the inverters that were used for energy storage were very similar to the ones that were used for solar. So, in terms of transitioning the technology from PV and using it for energy storage, it was fairly easy for a lot of these companies to do, and we saw a huge pickup in the DC block approach going on in our space, where we usually would build out project with a battery from a particular supplier and a central PCS from a different vendor and put these two together. Now, the challenge there is that you really require a really tight integration and coordination of these two components. These are one of the two most critical components in a battery system. You can talk about other auxiliary ones like cooling and management system and data collection, but really the main part, I would actually even say that the inverters and the controls are even more important than the batteries themselves. The batteries at the end of the day are passive devices that are just storing energy and acting upon the command of the inverters. So it became really important to make sure that when you deploy a site of this size, where you have more than 100 inverters, more than 400 DC block containers on site, it is extremely important that every inverter and every DC block container is communicating and coordinating with the grid, with its internal controls in the right way, that you're getting what you need at the point of interconnection. Now, those challenges were definitely eliminated when you come to an AC block, where the inverter is actually integrated into this container. So you're doing all this testing already in the factory. You know that it's going to work. Your firmware and softwares are all tuned up, and you just drop it on site. And it's a more plug and play approach. This definitely brought in a lot of advantages on the AC block side, with lower integration cost, much quicker installation and commissioning times, whereas the DC block obviously took a lot more time to be tested on site. Commissioning took a lot of time. It also took more to like deliver and install and individually connect these inverters to all the batteries as well. Another big difference that we were seeing is in terms of availability and performance. So with the single central PCS connected to a DC block, you obviously have a single point of failure, right? So you lose an inverter, you not only lose one battery, but typically they're connected to multiple DC blocks behind it. And you have a huge hit to the availability of the site, and you could lose an inverter due to miscommunication or other faults that the inverter has, or improper integration with the EMS as well. AC block approach typically offers a much higher availability, as you have these central inverters that are split up into much smaller inverters that are overseeing a much smaller DC battery. So if a DC battery has an issue, or if the inverter has an issue, you could basically take a much smaller portion of the system online and continue to operate at a much higher availability. We're seeing this more and more today, where utilities especially are getting very, very stringent with how good your battery performance and availability should be over a particular season or over a particular period of time, typically a year. And availability metrics are going to be going up, right? Because you have more and more renewables coming into the grid. Capacity is a very scarce resource, and it is really important for utilities to have capacity when that can be called upon and be operated at its full potential. So availability is definitely something that we are seeing as a really, really big differentiator across like different battery vendors that we see today. Obviously, in terms of on the commercial side, it's a lot easier to contract. It depends on what is the preferred approach in terms of contracting with multiple people. You could definitely reduce the system cost in that sense, whereas a single supply contract where the OEM basically packages the DC batteries and the AC part together does come at a cost premium, but is a lot easier to deal with in terms of performance guarantees, warranty, services, or any issues that happen over the course of the project. And operations and maintenance as well. You obviously have less points of failure with the central PCS, but you do have a larger single point of failure. That's the only difference. And I've experienced this personally in a lot of projects where I've worked, where when you work with equipment manufacturers that are different and you have faults that occur, it's really difficult to trace whose fault it is and try to resolve that while your system is down, right? So there's a lot of issues that happen where fault tracing and resolution takes a lot longer with DC block architecture, whereas the AC block approach is a much more tighter integrated product that gives you a bit more peace of mind because it's a single OEM that typically handles the operation of that asset. All right. That was a bit on the innovations that we are seeing in terms of battery cell technology and system architecture that is being prevalent on the utility scale space. I'll move on to obviously when it comes to technical considerations, I could devote a whole session to this. Due to limited time, I wanted to talk about just a few high-level things that I feel are very important when we talk about designing and sizing battery energy storage systems for utility scale development, right? When we talk about battery sizing, this is a typical site that you see on the bottom left here, where you have a PV array. These are battery containers spread out across the site, inverters paired to a few battery enclosures. All of that is stepped up by a medium voltage transformer, goes to the substation, which again steps that voltage up to something that's appropriate to be delivered to the grid, right? So when we look at sizing a battery, what we talk about is utilities usually come with, hey, we want 100 megawatt battery that can deliver energy for the next, that's capable of discharge. We need connection. Really look at various orders and all connection, right? So when I first started working in this space, there's the nomenclature of this was still pretty new, right? There was no set standard on what nameplate energy is, the usable energy is, but I found this really good schematic that shows, what is the appropriate usable energy metric to use when you're actually sizing a system for the grid, right? These are not just a system with a single container or 10 containers. If you're not able to use the right usable energy metric, and when you scale this across a project that has 100 of these containers or 500 of these containers on site, the difference in capacity that the system can actually deliver gets really, really large. So it's really important to know what are all the losses, all the way from what the manufacturer states that the DC nameplate energy of a system is, what are the efficiencies within that enclosure, what's the charging efficiency of the cell, what's the discharging efficiency. In most cases, lithium ion, you do not get to use the entire 100% state of charge range. We call it depth of discharge. So that's one of the things that I'd have to consider as well. So I think we're running out of time, so I'll quickly go to one other topic that is much more interesting, which is on commentary on ESS supply chain and the commercial side. I think we'll have some time after we get back to the main session. We can go into the other slides as well and have an open discussion. But when we talk about the commercial side, right? Batteries typically, when we build a project of this size, they constitute 70% of the total capex for the battery project. And the battery cell is one of the biggest cost components of the battery itself. And battery cells are directly tied, the cost of these cells are directly tied to the lithium carbonate supply and demand imbalance. Just a few years ago, with EV demand sentiment really going in the world, the market actually experienced a huge surge in raw material pricing of lithium carbonate, which had a major downstream impact on all the systems and projects that we're building, right? Because of how sensitive raw material prices are to the cost of the cell, which again flows down to the total cost of the system itself. So the elements such as the inverters and the construction cost and O&M and the balance of system are really much, much smaller compared to the cost of the batteries itself. And what really happened was there was a lot of positive sentiment in the industry on EV demand going up and people wanting more and more EVs. There was an expectation that there will not be enough supply of raw materials, which is especially lithium carbonate from the mining suppliers. And this really naturally pushed up the price, where all the batteries for grid scale applications and EVs started to go really high. And we had to experience what we called, we had to really push projects, advance them to like much later dates. And then last year or so, these inventories actually started closing the gap with demand. We're actually at a time today where the supply chain for lithium carbonate has matured a lot more. The supply inventories are somewhat actually at a much more surplus, where prices are at their lowest right now. So this is really one of the things as a developer, we look at planning projects 2 to 3 years down the line, and lithium carbonate and how that trends over time, how does the EV market impact the energy storage market, is actually a huge driver for the cost of our projects as well. Is there going to be enough raw materials? That's not a concern right now. I think what's the biggest concern is how volatile these prices are going to be in the future, because at the end of the day, we don't want these cost increases to pass to the end customer, which are the residential customers who are buying this energy from the utilities. You still want it to be at an affordable rate of electricity, where people can still, switch over to renewables, but not at a cost that is too prohibitive for their living expenses. In terms of commercial side, the utility scale industry has actually experienced a lot of headwinds in terms of regulatory policy that we've had to deal with in the past couple of months. Obviously, the US wants to onshore a lot of, especially with keeping the transition to renewables, they want to onshore a lot of manufacturing in the US. And the US President Biden actually announced a tariff rate on all EVs and non-EV battery supply chains, right? So we were looking at a scenario where come 2026, we would have a huge 25% tariff on all batteries. Okay, the risk management for that, we looked at, okay, can we get a domestic supply chain in place? Can we switch over to cells that are made in the US? And there were also other restrictions on forced labor arrangements that the US government was tracking with this few Chinese cell suppliers and preventing them from operating the US. So if you look at the graph on the right, where we think about how easy is it to switch over to US supply, we still see that China has a huge grip on the market, right? So almost 70% of lithium ion phosphate batteries for the grid application still comes from China. And it's really hard to make this decision where we could quickly transition over to something that's made in the US. And so this is still an evolving thing, and something that the industry is battling right now. And how do we navigate this over the next couple of years is something that it will be challenging and exciting to see. I think we can make a move to the main session. I think we will probably come back for a few more questions, and I think it's an open forum after this. So I have like one more slide to go through, and I'm really interested to hear what you guys have working, your thoughts that you guys have working in this field as well. So yeah, I think we'll jump back to the main session, and I'll resume once we're back here. Thank you.